right? So a omega cos omega t plus phi becomes the velocity as a function of time. So from this you can see that the maximum speed is equal to a omega. Okay. And differentiate this one more time, or second derivative of x with respect to time gives you that the acceleration is equal to minus a omega square sine omega t plus phi. So that also shows us that the maximum magnitude of acceleration is a omega square. Okay. And also we can see that there's a phase difference of pi by 2 between velocity and displacement, and a phase difference of pi between position and rather position and acceleration, or displacement and acceleration. Okay. Now the next important thing that we've seen is that if you take equations 1 and 2, this one, you can see that at t equal to 0 initially, that is, okay, from equation 1 and 2, the position is a cos phi, sorry, a sin phi, and the velocity, the initial velocity is a omega cos phi. So now using these two equations, we can find out the relationship between amplitude capital A and x naught and v naught, and phase constant phi, and again between x naught and v naught. So we can find amplitude in terms of what we call the initial conditions. That is, what is the position it's starting from, or what is the displacement from the mean position it's starting from, and what is the velocity with which it is starting. So that comes out to be, if you use sine square phi plus cos square phi as equal to 1, from that identity, you get that amplitude is equal to square root of x naught square plus v naught square by omega square. Okay. This comes by taking equation 1, squaring it, and taking equation 2 divided by omega on both the sides, and then squaring that. So if you square these two terms, you'll get this. Okay. And similarly, you get phase constant phi again in terms of initial conditions x naught and v naught. So that comes by dividing the two equations. We get that phi is equal to tan inverse of x naught divided by v naught by omega. So it becomes like this. Okay. So these two equations also become very important for us, because they tell us how to calculate the initial, how to calculate the phase constant and the amplitude of the SHM by just substituting what is happening at the start of the motion. That is, what position it's starting from and what velocity it is starting with. If we know these two things about the SHM, we can understand the phase constant and the amplitude from that. Okay. So anyhow, you have seen these things in the last lecture, but just go through this once as a quick recap. Then we will see questions based on this. So what we mean by kinematics of SHM is that equations of motion related to SHM, that how we describe the motion in an oscillation which is harmonic through equations. So these are the equations how we describe x as a function of time, v as a function of time, and acceleration as a function of time. Of course, x can be replaced with y or z, whatever, but it's a one-dimensional parameter. And similarly, the sine can always be replaced with cos and vice versa, because sine and cos are the same function. They only have a phase difference of pi by 2. Okay. So anything that is related to kinematics, that means in anything where we are not discussing about the force or dynamics or work energy or any application like that, but we are only understanding the motion. That is, what are the equations of motion, what are the parameters of motion. So any kinematics related solving in SHM that we are doing, these are the equations we will require. Equation 1 and 2 primarily, and also equation 3, which is the acceleration. So when you get questions related to kinematics of SHM, the main thing in these questions is determining the amplitude and the phase constant, or the frequency from that, or whatever. So we'll see some question examples like that. So let's move on to an example. So now, typical type of problem involving this kinematics of SHM. So we have something like this, that a particle in simple harmonic motion with an amplitude of 2 millimeters, okay, along the x-axis, and along the x-axis with mean position at x equal to 0. And a frequency of say 4 hertz. So it makes 4 oscillations per second. Starts
Sir, y-axis or x-axis?
x-axis, x-axis. It starts from the position x equal to plus 2 millimeter, sorry, plus 1 millimeter at time t equal to 0. Okay. And also moving towards the mean position. Okay. So calculate its angular frequency and phase constant. Write the equation of SHM. Okay. And determine the earliest time when it stops momentarily. What is the earliest time at which its velocity becomes 0 momentarily? And we'll also determine the earliest time when its acceleration is equal to 0. Okay, so as you can see, this question is not dealing with anything to do with force or energy. So it's only dealing with the equation of motion of SHM. So it's what we call a kinematics of SHM problem. So we have to solve it using those equations that we've discussed above, and using those conditions that we discussed, that the amplitude and the phase constant, how they depend on the initial conditions. So using that part, we have to find this out. Okay. So just try this out. We'll do one more thing here. We'll also determine its initial velocity. Initial position is given to us, it's plus 1 millimeter. But what was the initial velocity with which the body was moving in the SHM? That's part of the first section. So just go through the equations that we've discussed about the kinematics of SHM and try to see that how all these unknown quantities can be related with those equations. So they are kind of interrelated to each other, the various parameters. So you have to understand how to take advantage of those interrelations from the given information in the question and find out the unknown quantities. So that's what this is all about. Yes, exactly. So that is the equation you have to use. Okay. So the relationship between frequency and time period and angular frequency omega, all these various things. Okay. In fact, I mean, while we are at it, let's find the time period also. Okay. So capital T is time period. Okay, so just a word of caution here. When we are writing the phase constant, people, we have to understand that the direction of velocity also depends on the phase constant. So it's not just that the position is a by 2. So sine phi has to be half, but it's also about the initial velocity. No? The initial velocity is what kind of quantity? It is negative. No? To understand that thing over here, because it's moving towards the mean position. So this is where this kind of question gets a little bit tricky. Okay. Anyhow, so let's see. So what one way
So
is
it
that
will be n pi plus pi by 6.
it will be pi minus pi by 6 because sine is positive and cos is negative. So
Oh.
that's second. You understanding? No? Okay.
Ah.
So one is, see, we can start with, instead of following any equations, any formula and all, let's just start with the equation, the general equation. So suppose I just assume x is equal to a sine omega t plus phi. So now what information is given to me in the question directly is given that the amplitude is 2 millimeters. Okay. Is given that the frequency is 4 hertz or 4 cycles per second. That means omega is 2 pi f. So it is 8 pi radians per second. Okay. And the time period is 1/4 of a second or 0.25,
0.25 seconds.
or we can also write it as 250 milliseconds, whatever. Okay. That's known. And what else is known? That my x naught is plus 1 millimeter. And one more vital piece of information, that v naught is negative because it is moving towards the mean position, towards x equal to 0, and it is at a positive coordinate. That means it has to be negative. So this information is equally vital. Okay. So now let's start plugging those things in here. So we can see
So
that
it is negative.
we can see that v as a function of time is a omega cos omega t plus phi. So according to my equations, x naught should be 4 sine phi, and that should be equal to, sorry, 2 sine phi. Amplitude is 2. So x naught should be 2 sine phi, and that is equal to plus 1. So that means my sine phi is equal to half. So that means phi in general is sine inverse of half. Now, as you know from trigonometry, sine inverse half does not have a unique solution. It has, within one cycle also it has 2 solutions. Okay. And the other thing is v naught is a omega cos phi. Okay, where of course this a omega term itself is 2 millimeters into 8 pi radians per second. So it is 16 pi millimeters per second. This is the maximum speed a omega. Okay. This is a omega. Okay, anyhow, so now this is this. Now from this information, what we know is that cos phi therefore has to be a negative quantity. How much it is, I don't know, but it's negative. Okay. So sine phi is half and cos phi is negative. So this tells me that phi should be in second quadrant.
So can you explain again why phi should be in second quadrant?
I've just written over here, beta, cos phi is negative and sine phi is plus half. So
No,
in
I
which
mean
quadrant that happens?
velocity being negative, sir. Velocity being negative, how can we conclude that it has to be in second? It can be in fourth also, third also.
बेटा साइन पॉजिटिव है और कॉस नेगेटिव है, थर्ड में ऐसा होता है क्या? थर्ड क्वाड्रेंट में साइन नेगेटिव होता है ना?
Cos negative किधर से है? मैं वो पूछ रहा हूँ. I didn't understand it.
है ना बेटा, आप ये देखो ना, साइन का वैल्यू कितना है? इज इट नेगेटिव? I've written it already ना, positive. How can it be in third quadrant or fourth quadrant?
So it can be in first or second. Okay, okay.
And cos is negative.
Okay.
Okay. It has to be in second quadrant na, because sine phi is positive and it's not an or condition, it's an and condition. Cos phi is negative.
Yes,
That only happens in second quadrant. Okay.
Yeah,
So
that I got it. That I understand. Yes.
Pi now becomes pi minus pi by 6 or 5 pi by 6. Okay. So now we've got all the parameters. So we can write x finally properly with all the values. It is 2 millimeters, okay, into sine. Or we can leave out the millimeters, we'll express that later. So it is 2 sine omega was how much now? 8 pi t plus 5 pi by 6. This is the full equation of SHM, where x is in millimeters and
Yes.
t is in seconds, because omega is in radians per second. Okay, and now from this we can also see that v is equal to 16 pi cos of the same thing, 8 pi t plus 5 pi by 6. Okay, so v is this, where v is in millimeters per second. Okay, so now we have got the first part. I think we have to calculate all these things. Time period also we found out. So omega 5 time period. Now v naught. Okay, so now v naught we can see from here. V naught is 16 pi cos of 5 pi by 6. So cos 5 pi by 6 is how much? It's minus root 3 by 2.
Minus
This
half.
becomes minus 8 pi root 3 millimeters per second. So the minus sign is just telling me the direction. Okay. So we are understanding this, like if you want to look at it like a visual picture, that this is your x-axis. Okay. So if this is your mean position x equal to 0, this is your amplitude position x equal to plus 2 millimeters, and this is x equal to minus 2 millimeters. Okay. Then the starting is happening exactly here. At t equal to 0, the object is here. It is at x equal to plus 1 millimeter, and it is going in this direction with a velocity equal to, I mean, with the sign convention, it is minus
Negative.
8 by root 3 millimeters per second. This is where the motion starts. Okay. Now we have to also find out the other things, that when it reaches the origin, when it reaches that side and all that. So that you have to interpret the question, the next part of the question. Okay. So the first part of the question is this. So this is amplitude on the positive side. This is amplitude on the negative side. You can see the time period is 0.25 seconds because the frequency is 4 hertz. So this kind of thing you have to be able to solve very efficiently, okay, from the given conditions. So that is why I told you that these things are very important. The relationship between amplitude and initial position, initial velocity, the relationship between phase constant and x naught and v naught. These two things are very important. Okay. One more thing you can be asked over here is the initial acceleration. Okay, so also from this you can see that acceleration will be minus a omega square cos omega t plus 5. So though the question is not asked, but initial acceleration is minus a omega square sine 5. So it is minus of 2 millimeter into pi square into 64 into sine 5 pi by 6. So the acceleration is positive, interestingly. Because the displacement is positive, so the acceleration is, sorry, the acceleration is negative. Okay. So the acceleration also points towards the mean position. So the initial acceleration will be minus of, this is almost like, pi square you can take as approximately 10. So 1280. So that's like 1.28 meters per second square towards the left. That is the initial acceleration.
Yes, sir.
So it's sin pi by 6 भी तो होगा ना, divided by 2
Go
होगा.
into half, correct.
Yes.
So there is a factor of half also. So it will become 0.68, 0.64 in meters per second square. Or you can write it as 64 centimeters per second square. Yes. Okay, now the next part of the question, you have to find out the earliest time when the particle stops. And we have to also find by the, and we have to also find the earliest time when the acceleration is 0. Okay, so let's check out the answers. Now see, third part, was it, or second part? Equation of SHM we've written, so third part, earliest time when it stops. Okay. So we've already got the velocity as a function of time. No? We've got velocity as a function of time as a omega cos omega t plus 5 pi by 6. Okay. So v is equal to 0 when cos omega t plus 5 pi by 6 is equal to 0. So that is when, now see, cos theta is equal to 0 means that theta is pi by 2, 3 pi by 2, 5 pi by 2, and so on and so forth. Okay. But here this term is already greater than pi by 2. So the earliest time,
3 pi.
yes, when t is equal to t1, let's say, so is when omega t1 plus 5 pi by 6, because time cannot be negative, so it has to be greater than pi by 2. So that's when it's 3 pi by 2.
Sir, can you
That
explain
means,
what 3 pi by 2 it should be?
when is cos theta 0? Tell me, for what values of theta cos theta 0?
Pi, n pi.
No, that is sin theta 0.
Oh, sorry. Pi by 2, sorry. N pi by 2.
Okay, understood now? No? Okay. Okay. So this becomes how much? 9 minus 5, that is 4 pi by 6 or 2 pi by 3. Is correct? Okay. So omega t1 is this much, and omega is how much? It is 2 pi upon time period. So that earliest time will become capital T by 3, or 1/3 of the time period. And the time period we knew was, how much was it? 1/3 of a second, 1/4 of a second. So this will become 1/12 of a second, or approximately this much time. So this will be the earliest time when it stops. Okay. You can also understand this visually. Okay. Alternatively, what you can do is, you can also understand that particle in SHM is at rest when it is at extreme position, plus minus a. Okay. So here x was a sine omega t plus 5 pi by 6. Okay. So if you think of the x versus time graph, now we had discussed about transformation of graphs and all that last time. So you realize that this is a graph like this, okay, where it's starting from a by 2. But going towards the negative side, or I mean having a negative slope, so it's, you know, like this. Okay. So the earliest time it stops will be here, this time, when it is reaching minus a. So this is my time t1. Okay. Now you'll realize here that this, from here to here and here to here, okay, this time is how much? This is the time equivalent to, the phase is going to pi over here. No? So if you look at a regular sine graph, y is equal to sine x type of graph. Okay. So where the 0 of this one is, that is equivalent to this position here, 5 pi by 6. Okay. And where this is t1 is, that is equivalent to this position 3 pi by 2. So this distance from here to here in terms of change in angle, it is 3 pi by 2 minus 5 pi by 6. So if this whole time from here to here is t1, you can see that omega t1 has to be equal to this quantity. It is the difference between 3 pi by 2 and 5 pi by 6. Because the quantity in this bracket, it is equal to 5 pi by 6 at t equal to 0. And it is equal to 3 pi by 2 at t equal to t1. So this is how you understand this equation, which we have written here also. Here also we've written this equation, how we understand it visually from the graph.
Okay.
Now, similarly, you have to determine the earliest time when its acceleration is 0. So that is also actually right there in the graph in front of you. You have to just identify it. Okay. So earliest when its acceleration is 0. This was the earliest when its speed was 0.
So this T1 is the earliest time, no?
T1 is the earliest time. Yeah.
Yes.
Which you've written here, then the value, it's 1/3 of a time period or 1/12 of a second.
Yes, sir. Sir, is equal to pi now, or earliest time, sir.
Yeah, so one more way to easily understand the kinematics of SHM is to visualize simple harmonic motion as a projection of a uniform circular motion. So this is a very interesting way to understand SHM. So if you think of any particle in a uniform circular motion, let's say in the XY plane, with the origin at the center of the circular motion, with a constant angular speed omega. So if this is a circular path which has a radius equal to capital A, this is the x-axis and this is the y-axis. Now let's say the particle started from this position at t equal to 0 and is going with a uniform angular speed omega. So its initial position at t equal to 0 would have been this as a vector quantity where this angle is, let's say, phi. But at
The
some
initial
time,
phase.
sorry,
Sir, the initial phase.
yes, that becomes the initial corresponding initial phase. Okay. So at some general time t, if the position is theta, okay, so you can see that theta will be equal to phi plus omega t, because at t equal to 0, the value of theta we have taken is equal to phi. So when we write the position vector in component form, you can see the x and y components are themselves SHMs. X component, or we write the position vector such that it is x I cap plus y j cap. You can see x is equal to magnitude of r cos theta. So that is a cos omega t plus phi. And similarly, y is magnitude of r sine theta. So that is a sine omega t plus phi. So these are both SHMs. These are both SHM with angular frequency or frequency equal to omega by 2 pi, time period equal to 2 pi by omega, okay, and all these things. So that's one way to visualize this. So as this particle is going round and round, you can see its projection on the x-axis. Or for example, we have taken the standard equation of SHM as the a sine omega t plus phi. So let's look at the projection on the y-axis only. So for example, when the particle is here, okay, its projection on the y-axis is here. Okay. When the particle is here, its projection on the y-axis comes here. Then by the time the particle reaches here, again its projection on the y-axis is here. Then by the time the particle reaches somewhere here, its projection has gone down. Okay. Then by the time the particle has come on this side, its projection has gone down and it's on its way up. So you can also see that if it is going round like this, then at this point of time, the circular motion's velocity is in this direction. So the projection's velocity is upwards. Okay. Whereas when it's here, the circular motion's tangential velocity is in this direction. So the projection's velocity is downwards. So like that, alternately is going up and down between minus a and plus a with the same time period and frequency as the particle is going the uniform circular motion. So our standard equation, the way we've taken it, is actually this one. But as I said, there's no difference between sine omega t plus phi and cos omega t plus phi. There's only a phase difference of pi by 2 between the two. So you can visualize it either way. So this is like the standard SHM. So now how this method makes it easy, I'll explain in a moment, but write this down first. Okay. So SHM is a projection of uniform circular motion. So you can see from this that both the X and Y projections of this uniform circular motion are SHMs. They're individually simple harmonic motions.
Sir, but they are not equal, right?
They have a phase difference of pi by 2. Their amplitude and angular frequency are same.
So what have you written in note? Projections of this?
Uniform circular motion, UCM.
Sir, can you explain that dotted diagram again?
The particle is going in uniform circular motion, and while it is in that circular motion path, we are looking at how its projection on the y-axis looks. So you can see its projection on the y-axis is going up and down. So that's a simple harmonic motion.
Acha, हाँ, yes sir.
Yes, sir.
Sir,
Yeah,
sir, can you explain once again about that?
yeah, we will understand with examples. Have you finished writing it?
Yes, sir.
Okay. Okay, so now, for example, this particular problem that we had, the one we were solving earlier. So in this, what is happening is that we were told that the amplitude is 2 millimeters, but the starting position was 1 millimeter, and my initial velocity was negative. How I knew this? Because it was moving towards the mean position. Okay. And the frequency was equal to 4 hertz. So instead of visualizing as an SHM to begin with, think of it like a uniform circular motion to begin with. Okay, but only you take your SHM axis as the y-axis because we are used to the standard sine term. Okay, so now if it's going around with omega like this in the circular path, so you can see that y is e sine omega t plus phi, or actually whatever, take this as your x-axis because this is given as x naught. So it's just a matter of visualization, what you're taking as your x-axis and what you're taking as your y-axis. Okay, so there's no problem with that. Okay, so this is your equation. Now in this, you can see that this amplitude is 2 millimeters. So this is x equal to plus 2, this is x equal to minus 2. So while the particle is going around in the circle with omega equal to 8 pi radians per second, the projection of the particle is going up and down on the x-axis. Okay, so where is x equal to plus 1 millimeter? It's here. So immediately you can see that your particle could be either here or here. But if it is here, then it would be going up. Whereas if it is here, it's coming down. Now we know that the initial velocity is negative. So that means the projection at t equal to 0, x naught is here, is downward. So that means the particle is here. Okay. So now you can immediately see that what will be the initial phase constant. The initial phase constant is nothing but this angle, no, phi. So this is very easy to work out trigonometrically, no? That if this is half, okay, and this is, so you can see immediately it's in the second quadrant. So you can see that the phase constant phi is equal to sine inverse of half in second quadrant, not in first quadrant. So you can see that it is 5 pi by 6. Okay, so that's done. Okay, now the thing is, the first time when it reaches the mean position, that will be this time over here. And the first time when it reaches an extreme position, that will be this time over here. So this is when its acceleration becomes 0. This is when its instantaneous velocity becomes 0. So these two are the things we had to find. Okay. So you can see that in terms of in terms of circular motion, what is the angular displacement from here to here? It is omega t1. So omega t1 is basically how much? Pi by 6, you can see, because this is 5 pi by 6. Okay.
Yes, sir.
And in terms of angular displacement, what is this one? This omega t2. This omega t2 is actually pi by 6 plus another pi by 2. So you can see it's 2 pi by 3, isn't it? And you can, so this will give you t2 as t by 3. Remember, that is the time we had got for the first time it stopped. And this will give you t1 as t by 12. And remember, this is the time we had got earlier. In that part, we had written this second one as t1 and the first one we had just written as t because the question was in reverse order. But you understood now, so how simple this becomes. You don't have to think of the sine graph and all that. You have just converted into a circular motion problem. So this is how you can make use of this concept, that not only it makes it easier for you to visualize exactly how the SHM is looking. You have to just imagine, like you can imagine the blade of a fan that is going around in a uniform circular motion, and you're seeing it from the side. So how the projection of the blade appears to be, or you're seeing the shadow of that blade on a wall, which is falling perpendicularly. So that shadow alternately increases, decreases, then on the other side it increases, decreases. So that is how the SHM actually looks. So now the thing is, it not only helps you in visualizing the SHM and physically understanding it, but it also helps you in directly solving problems like this faster at the exam level. Okay. So this is very important, the method of determining kinematics of SHM from the projection of uniform circular motion. So hope this is clear to all of you. So first and foremost, how we got the phase constant, and then we got the earliest time when it's at mean position, acceleration is 0. And this is the earliest time when it is at 0 velocity, or it is at an extreme position. Okay, so this is about that projection method. So with this, we complete the first part of SHM, which is about kinematics of SHM. Now we come to dynamics of SHM, that is to do with forces. And also we will see application of work energy.
So here we'll discuss F is equal to kx, no?
Yes. Okay. So we have already seen from the kinematics that if x is equal to a sine omega t plus phi, then the acceleration, which is d2x by dt square, is minus a omega square sine omega t plus phi. So if you compare this equation and this equation, we come to the very important relation that the acceleration, or what we can write as second derivative of x, is minus omega square x. Okay. So that means the net force is minus m omega square x in SHM, where F is the net and it is restorative in nature, and x is the displacement from mean position. And of course, m is the mass of the body or the particle which is doing the SHM. Mean position is x equal to 0, and m is the mass of the object. Okay, so this is the force equation. So, or we can say that F is equal to minus kx, where k is a positive constant. It is called the force constant. In the case of a spring mass system, it's nothing but the spring constant actually. So k is equal to m omega square. So this is the dynamical condition for SHM. This is what we require in terms of force.
Sir, m omega square, no?
Yes, m omega square. That's what I've written. K is equal to m omega square.
Yeah.
Okay. So this is the dynamical condition for simple harmonic motion, that the net force acting on the particle or the body must be equal to negative of some constant into the displacement minus kx. Then that constant k will become m into omega square, where omega is the angular frequency of the harmonic motion and m is nothing but the inertia or the mass of the body. Okay. So the dynamical condition is basically that restorative force is proportionate to displacement. Restorative means that the sign is negative, and proportional to displacement means that its magnitude is proportional to the magnitude of displacement. Okay. So any system that shows this property, whether the force is coming as a result of elastic force from a spring, or it is coming as a result of some electrostatic force, some gravitational force, some combination of external forces, whatever be the cause of the external force. But if it satisfies this condition that it's a one-dimensional system where x equal to 0 is a stable equilibrium position. So the net force is 0 at x equal to 0. And the moment you displace it from 0, it gives you a force that is proportional to x but opposite in direction. So the further away, proportionately, the more the magnitude of the force, but the direction is always towards the mean position. So that's what we mean by saying that it's restorative. It's always restoring it to the mean position. And by proportionate, we mean that only, that with the magnitude of displacement increasing, the magnitude of the force proportionately increases. If I double the displacement, the force's magnitude doubles. If I triple the displacement, the force's magnitude triples. Okay. So this is the requirement in terms of force. So that's why it's called the dynamical condition. Dynamics is to do with force. Okay. Samarth, you want me to scroll up to the previous question? Okay. So we'll finish writing down this part for everyone. Then I'll just take you back to the earlier question for a moment.
So you have written restorative force, na? Restorative force.
Which one? Restorative force.
Restorative force.
Restorative force, remember we had discussed in work by energy also.
Yes.
A force which is in relation to stable equilibrium position. It always points towards the equilibrium position. That sort of force is a restorative force. Spring force is an example of restorative force. Okay. Acha, Samarth, I'll just take you back to this. Just go through this once. If there's any doubt, let me know. You can note it down later. Also, I'll send you the notes. Okay.
So 1 second.
So yeah,
One
which
second,
part?
sir. Could you go back up?
The UCM part?
Yes,
This
same
question?
part.
Okay.
Done, sir. Thank you.
Okay, done. Okay. Right. So now, as our first example of dynamics of SHM, we will see SHM of a spring mass system in horizontal orientation. So this is the simplest dynamical example of SHM. So of course, remember, for any oscillation, there should be no non-conservative force. So if the mass or the block in concern is oscillating on a horizontal surface, by definition, that horizontal surface must be frictionless. If it has friction, then it will not be an SHM because there will be dissipation of energy. Oscillation itself means that the energy remains constant throughout. It keeps oscillating between potential and kinetic energy. So on a frictionless surface, a block can slide freely, but it is also attached to a spring, an ideal massless spring like this. Okay. So if this is the natural length of the spring, then we can see that on either side, if we either extend the spring or we compress the spring in comparison to its natural length, we can see that it will create a restorative force which is proportional to displacement. So here, if the block is given a positive positive displacement, then it experiences a spring force in the negative direction. And similarly here, if it is given a negative displacement, then it experiences a positive force. So in either case, we can see that the spring force is equal to minus kx. And that means mass into acceleration is equal to minus kx, where acceleration is d2x by dt square. So in this position, the block will tend to have an acceleration like this. In this position, the block will tend to have an acceleration like this. Okay. So we will have acceleration equal to d2x by dt square is equal to minus k by mx, where k is the spring constant and m is the mass of the block. So any system like this will have a fixed value of time period. So compare with the standard SHM equation, d2x by dt square is equal to minus omega square x. So omega is square root of k by m. So time period, which is 2 pi by omega, is 2 pi under root m by k. So that means the frequency and time period of such a system, frequency and time period of this system is determined from the spring constant and the mass only. It is not affected by how much amplitude the block oscillates with or what the initial phase is. That is the first important thing to understand. Okay? Only, and it is therefore independent of amplitude and phase constant. So for example, if the spring constant is, let's say, 20 newtons per centimeter and the mass of the block is 5 kilograms, then the time period of oscillation will be 2 pi under root m by k, which we'll have to convert to SI unit here. So 5 kg divided by 20 into 10 raised power 2 Newton per meter. So this pi by 10 that we'll get will be in seconds. So this time period of approximately 0.314 seconds, this time period is going to be the same no matter how much amplitude or what phase constant the block is oscillating with. Whether it's oscillating with an amplitude of 1 centimeter or 2 centimeters, it will not affect the time period with which it oscillates. The time period is only determined by the spring constant and the mass of the block, which you can see are the fundamental physical properties of the system. One is the elasticity of the spring of the system, and the other is the inertia of the block. So these two fundamental physical attributes determine how fast the block is oscillating or what frequency it is oscillating. The frequency is 10 by this thing hertz, so it's approximately 3.2 hertz. Okay, frequency can always be in a like fractional value or decimal value. It need not be a whole number, because it could be that the oscillations are such that per second it doesn't complete an integer number of oscillations. It completes, in this case, 3 point oscillation. So that means 3 and 1/5 of an oscillation. So frequency need not always be a whole number or a natural number.
So
That is the
that
most
is
important
determined,
thing to
no?
understand. Sorry,
Sir, is determined, no?
is determined from only these two things: the spring constant and the mass. It is independent of amplitude and phase constant. So
So
what
it can
actually
be,
determines?
so
Yeah.
time period equation can be related to this 2 pi root of L by G. वैसे ही है ना, वही form में.
But that is like a case of pendulum. No? So pendulum does
Yeah.
what is called angular harmonic motion. Its motion is angular. No?
Okay.
So, but we will see, yes, that that also comes from this kind of equation only. Okay, because that is also a harmonic motion. The only difference is there it is angular motion which is harmonic. That means the angular displacement is a sine function of time, and this is a simple harmonic motion. So the linear displacement is a harmonic function of time. Harmonic means sine function.
Okay. Yes, sir.
Okay. Okay, so this is clear. So amplitude and phase constant are determined purely from the initial conditions. And by initial conditions, we always mean the initial value of x and the initial value of v. So for example, suppose we are starting the motion in such a way that the block was initially at the mean position, and to set it off into motion into an SHM, what we do is we provide some kind of impulse, like maybe something comes and hits it in a collision kind of effect from one side, or we just apply a rapid impulse, a sharp impulse, like when you strike something sharply. So, so initially at t equal to 0, okay, the extension of the spring is 0. It's at natural length. But now, at time t equal to 0, a sharp external impulse acts like this. Okay. So given that the mass of the block is this time, let's say 10 kilograms, okay, and the spring constant this time is, let us say, 10 newtons per centimeter, and initially the spring is at the relaxed state. Now a sharp impulse acts horizontally. Let's say the magnitude of that impulse is 0.2 Newton seconds or kilogram meter per second. So this kind of impulse acts horizontally at t equal to 0, setting the system off into an SH. So find frequency, time period, and amplitude of SHM. Okay. Also write x as a function of time, where x is the extension of the spring. Okay, so when x is positive, the spring is extended. When x is negative, the spring is compressed. So we are taking that kind of sign convention that x is here, the displacement from the natural length position of the spring, such that positive when the spring is extended and negative when the spring is compressed. Okay. So this is the first level of dynamical question in SHM, where first of all, you have to apply the free body diagram concept like we did above, or just use the standard formula for the horizontal spring mass system that you know from that FBD. So either side, when the displacement is x, the force is equal to minus kx. So comparing that with standard equation of SHM, you know the value of omega, time period, frequency, all these things. Next is, once you know the value of omega, from the given condition, you have to determine what is your x naught and your v naught, and you have to determine the value of amplitude and phase constant from that, so that you can write the equation of x as a function of time. So again, basically your omega is coming from the physical properties of the system, which is k and m, the elasticity and the inertia. Whereas your phase constant and amplitude, they will come from the initial conditions. That is how we are setting the motion off, how much displacement we are giving, how much velocity we are giving at t equal to 0. Yes. Yes, Piyush, that's correct. Okay, for omega. Okay, Piyush, correct. Samarth, correct. Okay, so let's finish off this question. So basically, I'm not repeating the free body diagram thing, is the same from above. So on either side of the mean position, if you displace the body, you will see that you will get this equation that the acceleration, which is d2x by dt square, will be minus of k by mx. Okay, so from that you can see that your omega square is k by m, or omega is equal to square root of k is how much now? 10 into 10 raised power 2 in Newton per meter divided by the mass, which is 10 kg. So omega is 10 radians per second. Okay, so that means time period is 2 pi by 10 or pi by 5, or approximately this much. Okay. And the frequency is omega by 2 pi. Yes, okay. So we got time period, we got frequency. Now amplitude and the phase constant also, that will come from the initial condition. Now you can see that just after applying the impulse at t equal to 0, just after the impulse has acted, what will happen is that the spring is still at natural length. So its x coordinate is still 0, it's still at the mean position. Okay. So x naught is 0, but it's got a velocity in this direction. So that velocity with sign is minus of j by n. This is from impulse momentum concept.
Yes.
Okay. So the impulse was 0.2 kilogram meter per second or Newton second, and the mass is 10 kg. So you can see the initial velocity is minus 2 centimeters per second or minus 0.02 meters per second, whereas the x naught is 0. So this thing we have to now use. Okay. So x naught is a sine phi. If we are writing x as a sine omega t plus phi, so that is equal to 0, and v naught is a omega cos phi, and that is equal to minus 2 centimeters per second. So you can see that sine phi is 0. Okay, it's sine inverse 0, but cos is negative.
Second quadrant.
Yes, so that means phi is becoming pi. So our phase constant is this. Okay, and also from this we can see that amplitude is square root of x naught square plus v naught square by omega square. So that is square root of 0 plus v naught is 2 into 10 raised power minus 2 square, and omega was how much? Omega was 10 radians per second. So how much is this making the amplitude? The amplitude is 2 into 10 raised power minus 3 in meters. That means the amplitude is 2 millimeters. So the phase constant is pi and the amplitude is 2 millimeters. So the equation of SHM is, it is 2 sine 10t plus pi, which you can also write as minus 2 sine 10t. Because sine of theta plus pi is minus sine theta. So you can visualize that the harmonic motion will be looking like this. It's a minus sign graph. So it starts from 0, but it goes to minus a plus first and then to plus a. So this is one cycle of the SHM. At quarter of the time period, it would have gone to the negative extreme, come to rest, then it will start coming back towards the mean position, crossing the mean position at maximum speed again. Okay. And that maximum speed you can see will be 2 centimeters per second. At 3/4 of the time period, it would have reached the positive extreme. And then at one cycle, it's back to 0. So this is the visualization of the continuing cyclical motion. Okay, people. So with that, we complete today's session. Hope this last question was clear to all of you. Okay. Yeah, Jagannath, what exactly you did not understand in the question? Please let me know. Okay, see what is happening in the diagram. You can clearly see the initial velocity is towards the left now. And how much is the magnitude of the velocity? It is impulse upon mass. Impulse momentum theorem, that impulse, net impulse is equal to change in momentum. So the object was at rest and you applied an impulse of J. So its momentum will have a magnitude of J by M and the direction is negative. So that gives you the initial velocity. Whereas where it started from the x equal to 0 position. So the initial x naught is how much? 0. Rest of it is the standard formula and equations that we've discussed today. Once you know x naught and v naught, you can determine the value of amplitude from that, and you can determine the phase constant, both the things from that. All right. Yeah, so as I was saying, that completes today's lecture. Now we've covered a lot of things today: kinematics of SHM and applications of that, projection of UCM as an SHM, and how to use that effectively in making problem solving easier. And finally, the spring mass system and dynamics. So please go through this carefully, and you can go through the solved examples from your module and HC Verma also of kinematics of SHM type questions as well as spring mass systems. So next time from here we will proceed about systems which have combination of springs. So please look up and revise the concept of parallel and series combination of springs. And from there we move on to vertical spring mass systems and then variations of that with pulleys and things like that. So a lot of your core mechanics concepts will also get revised along with that. Constraint relations, system of pulleys, those kind of things. Okay. Multiple spring systems, equivalent spring constant, etc. And with that, we will complete SHM and move on to the angular harmonic motion part, where we'll discuss about pendulums. Okay. No, Shivam, the password of lecture 1 recording is correct. I've checked it myself. The only thing is whenever you see a symbol like L in the password, be a little careful because it might be capital I or it might be L. So try both of them. Okay. Whereas one looks distinctly different. Or one thing you can do is you can directly copy paste the password. If you're using a laptop or a device like that, then you will not make a mistake in the password. Okay. But be very careful with the password. If there are dots and question marks and other symbols, alphanumeric symbols, use them. The letters are case sensitive. It's a cloud generated password, so I cannot change it. Okay. So capital letters, small letters, exclamation marks, alphanumericals, all these you have to be careful about. And particularly L, small L and capital I looks the same. So just try both the options. Okay. Anyhow, so that's for today's lecture. We are meeting one more time this week. So until then, have a nice time, people. Bye.
Thank you, sir.